Good morning, good afternoon, good evening, wherever you are. Welcome to this parallel session. We have 7 talks scheduled. As a reminder, we have the meeting chat available for questions. So if you think of a question at any time, go ahead and put it in the meeting chat, and we'll get to those at the end. Also, you'll be able to raise your hand. With that, let's go ahead and get started. Our first speaker today is Davide Keitel, who will be talking about a convolutional neural network search for long-duration transient gravitational waves, as shown here. So, Davide, go ahead.
Okay, thank you, Peter, and thanks for having me open this session. So this is a talk based on the PhD work of my student Luana M Modafferi and another recently finished PhD student, Rodrigo Tenorio. I'll give it on mostly their behalf, mostly their results in this talk. So let me start by defining what do I mean by these long-duration transients. So long-duration GW transients, the idea is that we're somewhere in this terra incognita between the short-duration transients from compact binary coalescence that we've already detected quite a lot of with LIGOVirgo Kagra, and then on the other hand, these very long duration, years or longer continuous waves from spinning neutron stars and other sources, which haven't been detected yet, but it's a very mature search effort that has been going on for decades, whereas in the middle, from like hours to months, there has been less effort, so it has been picking up quite a lot in recent years. And there's a variety of interesting signal types in that, mainly from neutron stars. There could be long-duration transients from newborn neutron stars, for example, binary neutron star merger remnants, and actually Joan-René will talk about those right after me. Then the main scenario I want to focus on today are pulsar glitches. There could also be different types of transient signals from magnetars or X-ray pulsars that are known to undergo highly energetic short-duration burst behaviors in EM and could have GW counterparts. And looking beyond neutron stars, there could be more exotic things like vector boson clouds around spinning black holes. So let's focus on the pulsar glitches. Glitching pulsars are this phenomenon where a pulsar is normally very stable in its frequency evolution, but at some point has a sudden jump upwards in frequency. They normally steadily lose a bit of energy by electromagnetic and hopefully also gravitational wave emission. But then some of the especially young pulsars undergo these glitches, which are sudden spin-up events followed by a relaxation phase, which can take a timescale of hours to months. The energy for that spin up, which means more energy, obviously cannot be created out of nowhere. So what we need to do is look into the depths of the neutron star, where the structure is mostly unknown. And there's lots of models for the pulsar glitches, but most people agree that there's a key role of the superfluid component in this. Some of these models also suggest that the glitch will be related to change in the overall quadrupole moment of the neutron star. For example, Yim and Jones discuss how a transient mountain could form, and that sort of models would then naturally give you a gravitational wave emission. So that's what we want to search for, and how can we do that? If we know there's a glitching pulsar, what can we do to look for the signal after it? So there's a simple signal model for this that was introduced by Reinhard Prix in 2011 called the transient continuous wave, slightly oxymoronic name, but the idea is that you start with a standard continuous wave signal model, which is defined by some phase and amplitude parameters like sky position, frequency, spin down, amplitude, and so on. And we add a set of transient parameters, which are in the basic form, the start time and duration of it. And then you simply multiply the standard signal model with a window function that could just be a rectangular cutout or an exponential decay, for example, with a defined start time and duration. And you get out this thing that looks like a continuous wave, but for a transient duration. And then you can use all the machinery that's been developed for continuous wave to search for these. I have this very busy slide with like a flowchart of the traditional approach to detecting it before our new convolutional neural network comes in. But to just give the very simple version of it, it's a standard merged filter approach. You start with 2 hypotheses, a pure Gaussian noise and a noise plus signal hypothesis. Then you compute the likelihood ratio for them, and you do some acrobatics with all these different free parameters. You first maximize over the amplitude parameters, which gives you the traditional F statistic, but now it's not the final detection statistic. It still depends on the start time and duration of the possible signal, and you need to evaluate all the possibilities, which can be quite expensive. And then you have different options like maximizing or marginalizing over this range of possible start times and durations. Either way, you get out some type of traditional F or Bayesian statistics, and you then evaluate those over a range of templates because you don't know exactly how your pulsar is behaving, even if you have an ephemeris you want to allow for some uncertainty around it. You have the results of the bank of templates, and you need to, by some method like one we developed recently, decide on the optimal detection threshold for that. So that's a traditional way, and it's already been usefully employed for real data searches and for estimating the future prospects for these type of signals. So we did a first open data search on O2, where we looked for Crab and Vela glitches. And then within the LVK narrowband effort, we searched for 9 glitches from 6 targets during O3. Unfortunately, not Vela, but Crab again, and the so-called big glitcher, JO537. From these 2 searches, there were so far no detections, and we haven't actually even beaten yet the indirect energy upper limit you can derive from glitch sizes, but we got closest so far for the Vela and J1105 pulsar, and then we extended an estimation based on these energy considerations to future run in a Moragas et al. Paper. So this is shown here. This is H0 or sensitivity compared against frequency. All the crosses are possible upper limits, indirect upper limits for pulsars, and then you see with future detectors, we dig deeper and deeper down into that. The curves are scaled by a realistic search sensitivity here. The best target by far is the Vela pulsar, which is known to glitch about every year and a half or so. It's been overdue for a while now, so we really hope to see that one during O4. Now I've come to the actual main topic, the search for TCWs, continuous waves with convolutional neural networks, which is in this paper on arXiv and very recently PRD by Modafferi et al. And the motivation, as I just said, is that the searches so far, even in the narrowband case, are computationally limited from having to try out these different start time duration combinations. But on the other hand, this idea of finding a transient continuous wave is basically a pattern recognition task in time frequency data. We know that convolutional neural networks are a great tool for recognizing patterns in general, or at least if those patterns are something like cats and dogs. Unfortunately, they are not actually quite optimal for this task of finding something that's very weak, narrow, and long-term feature or track, which has been nicely elucidated in a recent paper on continuous waves by Joshi and Briggs. And then on top of that, the transient part is actually more difficult than the purely continuous wave. So what we did here as a first approach is a hybrid approach where we still run a matched filter, but actually only the cheap version of it, and feed some intermediate data products to the CNN. So we don't work on the raw strain data, but on these intermediate data products. What are those? They are called the so-called F-statistic atoms. So we start from short Fourier transforms of the data, the standard LIGO data format, and then what the F-statistic does, it follows for each possible template the track and sums along this correctly Doppler demodulated track using also antenna pattern weights. And then that means that as intermediate products for computing the statistic, we have per SFT 7 quantities, which includes the projections of the data onto the templates and a set of numbers that basically quantify the antenna pattern of the detector. And from these, you can recompute the traditional statistics, or after we've run this once over the full duration without bothering about the different time combinations, which is quite cheap, we can feed these to a CNN. Now I'll talk about what we use as a CNN and then the results we find. So we built something quite simple where we use 1D convolutional layers, which are basically 7 pixels wide to account for the 7 dimensions of the atoms, and then slide along the time duration. We have only a handful of convolutional and then fully connected layers. And one main thing is that the output of the CNN is not a simple yes/no detection question, but it's an estimator floating number for the signal to noise ratio rho of the signal or not signal that it sees in its training data. We also use a curriculum learning strategy, which was previously employed in several other gravitational wave applications, where we first train on strong signals with high signal to noise ratio and only then add the weaker signals when it's already confident about detecting the basic shape. We then trained 2 different CNNs on the same noise samples, but one specialized to exponentially decaying window signals and one with the rectangular constant amplitude case. We also do something we call 2-stage filtering. The idea is that the simple approach of a standalone CNN, where you completely replace the computationally expensive partial sums of atoms, would go from an SFT I don't know if you see my pointer, from an SFT to the atoms. Then you apply the CNN, get a row statistic SNR, and ask if you have a detection or not. The two-stage filtering is you apply this still to all the templates, but then you pick the most interesting ones and pass them back onto the traditional calculation of the F and B statistic to get out just a few % more sensitivity on the top candidates without having too much cost. With that, overall, you still have an 80 times gain in speed from the CNN plus a short follow-up at the end, compared to doing brute force traditional statistic over the full template bank. And that's even if we compare with a PyCUDA GPU implementation of the traditional statistics that I did a few years ago. It's not that the CNN just profits from running on GPU. Then I come to my results. So first, it's important to say that we trained on a combination of synthetic, simulated, and real data taken from the O2 run. But then the tests here shown are the purely realistic case tested only on real data, which was data right after this 2016 glitch of the Vila pulsar. The first set of results on this slide uses an injection set which goes to quite high SNRs from 4 to 40 and split between the two possible rectangular or exponentially decaying windows. On the left, you see basically the SNR recovery as we're training it as an estimator for the SNR. It's a good question. Does it follow that diagonal line between injected and recovered? On top is the traditional statistic. On the bottom, the CNN. On the left, rectangular. On the right, exponential. And you see that it works quite well. Actually, on top, the standard one loses in the exponential case because for speed up, we only recovered with the cheaper rectangular case here. But the CNN, which is always cheap, recovers always well. And then from that, we get the receiver operating characteristic, comparing injections and pure noise, detection probability as a function of false alarm. Again, for the two different injections, there's a lot of curves here. So I just give you the main message that the black curve are the traditional statistic and the dotted curve is, I think so black is the traditional, dotted is the CNN with a two-stage approach. Here now it's the orange dotted, and you see always as you go to low PFA, which is a realistic, interesting case for real searches, we approximate the traditional statistic within 1% or so. And then what's even more interesting is, can we actually reproduce realistic upper limits? So we rerun with the CNN on this O2 data and did the injection set matching the one that I used back in 2019 for the original amplitude upper limits. They're shown here as a function of tau, because for short duration signals, you have weaker upper limits. For long duration signals, they get stricter, but actually correspond to roughly the same amount of energy that the glitch would put into a signal. And then we see that the CNN, which are the colored lines, very nicely almost matches the traditional approach as well again. What's important to note is that the injected amplitudes here are overall quite weaker than in the set used for the ROC curves before, because when you set upper limits, you really say what is the, I think in this case, it's 90% of how many you can recover with your search. That means you want to push quite deep down, so it's a more realistic test. And here what we find is that with the two-stage filtering, we still haven't quite approached the traditional only. We're within 6 to 7%, but it's quite decent, quite close, and as I mentioned, a lot faster.
I have about 2.5 minutes left.
Thank you. I only have 2 more slides, so that should work out well. So then there's a sort of side idea or look out to future projects where we tried out CNN parameter estimation. Can we do something more than just detection? So if in addition to estimating the SNR, we also estimate the duration of the signal by adding another output to the final layer of the CNN. And then we treated this more as a proof of concept. We were mostly interested in detection performance, but wanted to test this already, but without pushing it all the way, fully optimizing it. So here we only trained on synthetic data, but we actually already test on real data. So we probably could get more out of this if we push it harder. And we find here, again, for the 2 different sets of injections, a recovery plot where the injected tau is on the horizontal and the recovered by the CNN is on the vertical, and we see that they mostly follow the diagonal, except for small bending in the exponential case. So overall, this works quite well with some scatter. Could be optimized in the future, but certainly shows promise that you don't only see, oh yeah, there could be a signal in here, but also know what kind of signal and know how to follow it up in more detail with something like fully Bayesian methods. So that brings me to my conclusions that we have done this training of convolutional neural networks as an application to the transient continuous wave signals from glitching pulsars, which is useful and interesting mainly because of the computational cost constraints of the traditional method. We have the best results when we do this two-stage filtering, where we apply the cheap CNN over the full parameter range and do a follow-up with a traditional base factor statistic on the loudest candidates. In a ROC curve sense, at low false alarm probabilities, we are within 1 to 2% of the detection performance rectangular, and a few more percent for exponential windows. That's a much lower cost. And we could reproduce the O2 upper limits on the actual data, extended them for the first time to exponential windows, and got within a few percent again of the traditional performance. Not quite there, but the main motivation is that we could scale this fast thing up to broader searches covering a larger variety of targets, possibly working in the future towards all sky, all frequency, all time searches with even more optimized methods. So complementary approach, the traditional statistics go deep, but this goes broad to broaden ways of finding some detections from the wider pulsar population and hoping for more of them in 04, especially from VLA, but maybe something else will surprise us as well. Thank you, and I would have time for questions.
Yes, you do. Thank you. Maybe I can get started. Okay, so the signal model allows both a step and an exponential relaxation in the frequency of the. Do I understand that? So you talked about the window function. Oh, what? This is a time domain window function, or does the exponential refer to an evolution of frequency following a glitch?
This is a time domain models. So we call it transient continuous because we still assume it behaves in frequency as a continuous wave, that it just has the gentle spin down, maybe 2-3 orders, the Taylor expansion that we use by default, guided by the electromagnetic pulsar ephemerides. And then on top, we put this purely amplitude modulation.
Okay, so this is the appearance of a CW, so temporary appearance of a CW signal. Okay, so it's a time domain. So does this mean you're not modeling a change in an evolution in frequency of the signal?
That is correct. So there could be complementary approaches for this. One is to use the Viterbi algorithm, which allows for some frequency drifting. Or the other, which we probably want to go to when we do this full all-sky unknown pulsar target search, where we would drop this intermediate matched filter step and do deep learning directly on the time frequency data. But with that, it will be very, very challenging to get so infinitesimally close to the traditional performance as we can here. So this is sort of the intermediate approach where you can still do more or less the same thing you do with the traditional methods, but faster. And if you want to go to more variability in the signal model, you have to sacrifice something.
I see. Yeah, because I was wondering, since you have the CNN, I mean, at least that stage, it seems like that can generalize to another, to a broader signal model, or I would suppose it could.
Yeah, not directly, because the way we've done it, it takes these F statistic atoms, which are the per frequency template outputs of the matched filter. So we still loop the whole thing over a template bank of a few 100,000 or million templates, which is why it's important to have this afterwards and very fast. Whereas when you go to something that directly takes this time frequency data, there's no concept of a template bank anymore, and you would save another orders of several probably orders of magnitude of computing time, but it will be hard to go to the deepest sensitivities.
Okay, let's see. Any other questions? All right, if not, thank you again. And we'll go on to the next talk. This will be given by Joan-René Mérou on GPU accelerated searches for long duration transient. Go ahead.
Okay, thanks. So today I'm going to be presenting the work I've done with Rodrigo Tenorio, Davide Keitel, and Alicia Sintes on a new method we've developed in order to search for long duration transient gravitational waves from newborn neutron stars, remnants of binary neutron star mergers. A bit of an introduction first. So neutron stars are supernova remnants formed from the core collapse of massive stars between 8 and 30 solar masses. They are very extremely dense objects, packing the mass of the around solar mass in a 50-kilometer radius. They are still a topic of ongoing research, so their structure, equation of state, or role in heavy element synthesis is still not well understood. That's why studying gravitational waves coming from neutron stars can improve our knowledge about fundamental physics. This figure here on the right side shows a possible structure of a neutron star, even though the inner structure is still not completely understood. So there are different ways in which gravitational waves can come from neutron stars. In particular, non-axisymmetrically splitting neutron stars can emit continuous waves or long-duration transients. These last ones are the topic of this work. In particular, we are going to deal with long-duration transients, which come from remnants of binary neutron star mergers. So not those coming from glitches from process, as David explained in the previous presentation, but those coming from remnants. So if we have a coalescence of binary neutron star system, then a newly formed neutron star can emerge with very high ellipticity and very high spinning rate. And this can emit these long duration transients which have a duration from hours to days. In order to characterize the evolution of these transients, we're going to use the millisecond monitor waveform model, in which the frequency evolution of these signals is given by this expression here, where this is the initial frequency of emission, this is the time since the start of emission, the spin on time scale, and the Bragg index. Notice that here are the approximate parameter ranges for these remnants, where the frequency is very high compared to continuous waves. The spin on time scale is from hours to days, and the Bragg index determines the emission mechanism of these gravitational waves. Then the Anetis method we have implemented is a semi-coherent method, which is inspired by the Altis transient half method. This last method was implemented here at the same university a few years ago in order to search for these long duration transients. However, we aim to improve the method make a new method which is improved thanks to better computationally efficiency and obtaining comparable sensitivities. In order to obtain this better computational efficiency, what we have done is to lower the computational cost, both by using less templates in order to reduce the search and writing the code in JAX, allowing for the use of GPUs and then much faster codes. The data we use are SFTs, so short-Fourier transforms, where the amplitude is processed into normalized power with weights, or number count, where the number count is another statistic we can use, which is a digitized version of normalized power. Then these long duration transients, they have this shape here, so frequency versus time, and they evolve like this in this way. Its template in the parameter space will define a trajectory, and then we can sum the normalized power or number count across the trajectory in order to normalize it in order to get what is the significance of a given track. Now, look at these figures on the right side. So these are a bunch of templates which have randomized parameters, and the sliced lines indicate the parameters of an injected signal. We see that with these random templates, those which have closer parameters to the injected signal have higher critical ratio values, where the blue star is the value one obtains with a fully targeted search. So following exactly the trajectory of the injected signal and seeing what is the critical ratio that one obtains. What we can see here is that the effect that the signal has on the parameter space is very broad. And what this means in practice is that we can reduce the amount of templates we need in order to search for the signal, at least compared to the previous Altis transient half method. In order to test this, we have implemented two template banks. The first one is the cubic template bank, where we have where we put the templates in a cubic grid in the 3 dimensions with n equal space points in each parameter, and then the uniform random template bank, where each parameter is sampled from a uniform pair in the parameter space. So we have just seen that we need less templates than the Altis transient half method. The other part is that thanks to the being implemented the codes in JAX, which is a Python library which allows for the use of GPUs and compilation of Python code, with this implementation in JAX, we can obtain much faster processing times per template. So compared to the transient half method, which took around 1 millisecond for our test searches, compilation with CPUs and compilation took around 0.3 milliseconds, but with GPUs, they were even faster. So 15 microseconds per template, which is 60 times faster than the transient half method. Moreover, with GPUs, we can test different batch sizes. So how many templates are processed at the same time? And we see that with larger batch sizes, the timing per template gets even lower. In order to test these methods and to test what sensitivity we could get, we have generated a population of 1900 simulated signals with fixed parameters, well, fixed amplitude parameters, but distances between 0.1 megaparsecs and 3.1 megaparsecs, where the amplitude of these gravitational waves in the millisecond monetary waveform model are given by this expression here. Then these signals have been generated over colored Gaussian noise following the advanced LIGO design curve. In order to search over these signals and to estimate sensitivity, we have produced searches using the previously mentioned template banks in these parameter space boundaries and testing with different numbers of templates in order to see what is the amount of templates or the density of templates we need in order to obtain optimal results. In order to determine if a simulated signal has been detected, we have studied what are the distributions of critical ratios we obtain on only noise, and we have implemented two detection criteria. First, if template parameters are too far away from those of the injected signal, then we discard it as a possible detection. And the second one is that a threshold must be overcome in order to, as a critical ratio must be overcome in order to classify a possible template as significant. In order to set up this threshold, we study what are the critical ratios we obtain on only nodes. So these are the maximum critical ratio one obtains on the simulated population, but with only noise and different amounts of templates. We see that the more templates we use, the higher are these maximums. We have chosen the threshold for different amounts of templates to be the maximum critical ratio we obtain, which is number of templates. So a template can only be significant if the critical ratio is larger, greater than the maximum critical ratio one obtains on only noise. Once we have set up a threshold, we have different distances, we can determine an efficiency for a given distance as the proportion of injections that we have detected for that given distance. Then, since we have different distances, we can, using bisection of our sigmoidal curves that follow the efficiency versus distance, we can estimate a detectability distance. So in this case, we have used the D90%, which is a which distance out of 100 injections, we would at least detect 90 of them. These plots here show an example of how we have implemented this. So this is for an example of using the uniform random template bank and 1 million templates using either normalized power statistic or number count statistic. Then the white dots indicate the efficiencies for a given threshold on a critical ratio. And we have made a partial sigmoidal curve where those points which have an efficiency above 0.8 in order to determine what is the detectability distance. Here we can see already that with normalized power, the detectability distances that we obtain are a bit higher than with number count. Then these are the main results we have obtained. So in order to understand this, first the zero mismatch are the result with a fully targeted search. So following exactly the trajectory of the injected signal and seeing what are the critical results with critical ratio we obtain. So it will give us an idea of what are the maximum distances we could obtain with this given data. And then we have tested using the qubit template bank and the random template bank for different amounts of templates. We see that the more templates that we use, the greater the detectability distances. And with 10 million templates, we see that our both template banks get to almost the best possible expected results. What it means in practice is that with 1 or 2 more orders of magnitudes of templates, we could get to the best possible results. And this means that we need less templates than the distance half method, because the distance half method requires at least 10 to the 10 templates for this same search. So we need orders of magnitude less templates. Moreover, we see that with the random template bank and cubic template bank, we have obtained more or less the same performances, and that with number count, the obtained detectability distances are a bit lower than those obtained with normalized power. So, in conclusion, we have implemented a method for search remnants of binary Neutron star mergers. We have studied what are the configurations of template banks that give us an idea of how many templates do we need to use in order to get to optimal sensitivities, at least for this particular case. The developed methods are an improvement compared to the distance half method, because first, we use a lower amount of templates, so less computational cost, and moreover, the computation is much faster per template, so at least 60 times faster than the distance half method. And so the computational efficiency of this new method is much better than the previous method. Future steps involve the use of more advanced sampling methods for selecting our templates, such as Marco Monte Carlo methods or nested sampling, which could allow us to get to even better sensitivities with perhaps even less templates. Moreover, we are interested in working towards the application of our newly developed methods to offer data once it becomes available. And we're excited for the detection of new binary Neutron star mergers, because that will give us a chance in order to test our methods. So thank you very much. That's it. Feel free to ask any questions.
Okay, thank you. Very nice. All right, we do have time for questions, so please feel free to ask. Well, how much do you expect to be able to gain from the template selection? Because it looks like you have a good method now. Is there some computational inefficiency with the way the templates are currently?
Computationally inefficiency in which way?
Well, when you talked about using Monte Carlo methods for template selection.
Yeah. So we have already implemented at least random walk Marco Monte Carlo method, but we still have to study what are the particular way to implement it to obtain the best possible sensitivities. So it's an ongoing topic of research we're doing, but more or less we saw that our test indicated that with Marco Monte Carlo methods, the detectability distances that we could obtain were better than with simple random template banks. So I don't have a particular number, but maybe in the future I will have it.
Okay, but then you see using this, applying this whenever there is a detected binary neutron star merger, because you're targeting the newborn neutron star then?
Yes.
And how, let's see, in the search method, you just need an approximate time for the onset of the signal?
Yeah, we have tested our population with particular starting time, so we haven't searched over a range of starting times, but for a single starting time, because we assume that more or less we would know what is the starting time of the emergence of this neutron star after the merger.
And then you're using okay, so 24 hours of data.
Yeah, maybe we will do tests with more time, because some of the signals we could see that they keep going after these 24 hours. So with more time, we could maybe get to better sensitivities.
Okay, no, I think that's fine. I mean, in terms of timing, let's see, trying to just picture the search here. But so you're allowing for a longish duration signal then? Let's see, you have a tau, okay, 10,000 seconds. So over the course of hours. And then, all right. So do you need to know, just thinking aloud. Do you need to know the sky location accurately to do this search? Does it rely on the?
So we have been studying that, and what we see is that the signal is not very well localized in the sky. So what the main thing is to look at the main effect is given by the antenna patterns of the detectors. So maybe in this figure here, for example, we can see that there are some dark areas and there are bright areas. Things are related more to the antenna patterns rather than. That's it. Looking at the sky localization was not that much of an issue.
Benjamin, yeah, go ahead.
Yeah, thank you. Very nice talk.
Thank you.
Could you go to slide 7 again, please?
Yes.
So I may have missed that. Do you assume that the eccentricity should stay the same for the 24 hours, or do you?
Yeah, we assume it's the same. Yeah.
Okay.
So it's like a fixed parameter. We only focus on the distance related to the amplitude.
I see. Okay, thank you.
Yeah, thank you.
Great. I think we have time for one more question if there is one. Okay, if not, oh, Davi, go ahead.
Yes, I could just follow up on Benjamin's questions. I think, Joan-René, can you mute? We're actually sitting in the same office. So what we've seen in both the pulsar glitch and this type of work often is that the exact amplitude evolution, which comes from things like the ellipticity, doesn't matter that much. You certainly lose some SNR, but you don't tend to catastrophically miss signals just because the amplitude evolves differently. Usually the phase fitting is the most crucial, and then the amplitude is important, but not fatal if you get it wrong.
Interesting. Thank you.
Okay, well, thank you, Joan-René.
Thank you. Okay.
All right, we can move on now to our next talk. Ian Harry will be speaking about, now we're switching gears from continuous wave or somewhat continuous wave gravitational wave signals to short duration mergers. So please go ahead, Ian.
Cool. Okay, so yeah, let me get started then. And first, maybe I'll provide the link from the one talk to the other and sort of point out that this is work that was led by my PhD student, Conor McIsaac. Unfortunately, he's graduated and gone on into industry, so he's not available to present the talk today. But he has previously done work that's overlapped with David Keitel, so providing the link with the previous talks on CW, although that previous work was in the context of lensing. So the work I want to sort of talk about today is a new method that we've been working on to potentially observe precessing compact binary mergers. Like I said, this is work that's been led by Conor McIsaac. You can see there in the bottom left, image courtesy of one of the LBK talks when they presented nice caricatures of everyone, and Charlie Hoy, who's also been active in this since Conor graduated. So let's see. Let's just try and set the scene a little bit. So, what is precession in compact binary mergers, and why is it a problem that perhaps I care about? So we know that compact binary mergers are described by a number of parameters. If we consider those intrinsic to the source, the masses and the spins most obviously are the two that are the ones that we care about. We have in the past, when we've searched for compact binary mergers, both within LVK and with searches outside the LVK, have basically always assumed that these angular momentum of the black holes, these spins, are aligned in the same direction as the orbital angular momentum. So this simplifies the search in a number of ways, as I'll sort of explain in a little bit, but it does neglect a lot of freedom. There is a reason to think that these spins could be aligned if you've got systems that are evolving in an isolated environment. It's very likely that the spins will be aligned with the orbit, but we could have systems that are formed by, say, dynamic capture, and in those cases, the spins of the black holes will have no preference. So the black holes could be going around like this, and the spins of the black holes might be pointed in different directions. Now, if these spins are misaligned with the orbit as the black holes go around, the orbital plane can precess around itself, the orientation of the orbital plane will evolve in time. Richard O'Shaughnessy does a great dance explaining this if you've ever seen it. So why is it hard to find these precessing signals? Well, an advantage when the spins are aligned with the orbit, when we don't have this precessional dynamics, is that all of the other parameters other than the masses and the spin, so the sky location, the polarization, the inclination, the orientation of the source with respect to us, the only thing they affect in terms of the signal that we see is that they'll either produce a constant amplitude shift, a constant phase shift, or a constant time offset, or some combination of the three. So if we're able to develop a search that can maximize or marginalize over these three shifts, we're basically able to easily search over all of the parameters that aren't masses and spins, so all of the orientations, sky locations, etc. And then the problem just becomes one of how can we create a set of waveforms, a template bank, referring to the previous talk, that can cover these two mass and these two spin parameters. And that's a problem that we've solved as of about 10 years ago. And that's worked reliably through the advanced LIGOVirgo-CAGRA era. However, when you add precession in, not only do you gain 4 extra angles due to the spin angles themselves, so you have rather than having 2 spin magnitudes, you have 6 angles referring to the 3 Cartesian components of both spins on both bodies. You also have to worry about the sky locations as well, because the way that the precession will appear to you will depend on where you're looking at the system from and how it's oriented with respect to us. So you kind of can't ignore any of the parameters at all, and you end up with a much larger parameter space, and it's really hard to sort of solve this. This is actually a problem that people have been looking at for much longer than many other problems in our field. There's some early papers exploring this, even that go back to the 90s. It's one that's kind of dried up recently, though. I think there hasn't been much work outside of something, things that we've worked on for probably 5, 6, 7 years at this point. So it's definitely an important problem and one that has been challenging to find a solution for. So hopefully we can, finally today present you a way that we've gone about trying to solve this. And just to sort of point out at this stage in the work we'll show here, we are targeting neutron star black hole systems. So really looking for things with very high mass ratios where precessional effects are most important. If you've been following some of the public alerts, you may have seen that there's been some events with PNSBH that are reasonably high, as well as the events that were there in 03. So perhaps a type of system that's also of much interest at the moment as well, given that we're all bored of black holes by now. So let's think a little bit about the method that we want to show. So our method is based off of a work from Fairhurst and collaborators, which itself kind of builds on work from early in the 2000s by Pamela Chambelasneri and others. And the idea here is that if you're only worried about the dominant mode, so the 2-2 mode, if you were considering the line spin binaries, there's some subtleties when we consider precession, but for those who understand what I'm talking about, I'm considering the 2-2 mode in the co-precessing frame, so no subdominant gravitational wave emission. You can model any precessing binary with 5 harmonics, so effectively the Y2M spherical harmonics. And these can be combined in different ways. And in the Pan work, they sort of said, well, look, you can express it in terms of these 5 harmonics. And then, as long as I know the masses and the spins of the system, the changing the sky locations and the orientations will just mean that you get different linear combinations of these 5 harmonics. And there might be quite a different number of ways you can add them up. But if you were able to search in that space of the amplitudes and phases of these 5 harmonics, you would be able to find precessing signals. This became challenging in practice because there's a lot of unphysical freedom when you start trying to do this, and it became very hard to actually gain any sensitivity in that method. The thing that the Fairhurst paper provided was kind of a different way of expressing these harmonics, where they were ordered in preference. So the first harmonic would be providing most of the signal to noise ratio in most of the cases. The second harmonic would then be, if there's a subdominant contribution, it's most going to be coming from this, and so on. It's sort of a Taylor series expansion, so that you in almost all cases there would be very little power coming from this fifth harmonic. But it is just a different way of expressing the sort of same formalism that was there in the earlier papers as well. The advantage here being, perhaps I wouldn't want to consider the third, fourth, and fifth harmonic. Perhaps if I was only using two of these harmonics to do my search, I might go from something that doesn't work to something that actually becomes tractable. And indeed, in that paper, they suggested that someone might want to try this out using, say, two of these harmonics as a baseline. And this method has been used to sort of understand PE results and look for evidence of precession in those results as well. So just to sort of illustrate this a little bit more, here's a few cases where we can see how these harmonics break down. So in the top left, we have a, hope people can see my cursor, probably not because my internet's rubbish.
We can, yes.
Cool, awesome. So yeah, here we've got a case there's very little precession in this. And the dominant harmonic, the zero harmonic, pretty much describes the waveform perfectly. There's a little bit of contribution from the others, but it's very small. And the leading harmonic pretty much describes the waveform. You can then go to systems like this one over here, where there is some sort of low-level precession, and we have these two harmonics. Each of these harmonics does correspond to an aligned spin waveform. So, there's no intrinsic precession in any of these harmonics, but because they're beating out of phase with each other, when you add them linearly, you can get this sort of overall precessional modulation as you add them up. Again, in this case, probably only the first two harmonics matter, and the third and the fourth are pretty much negligible. You could have a case like this, though, where, again, very similar, the first three harmonics are in play here to get quite an overall precession. I think they struggled to find a case where the fifth harmonic actually mattered, but we can see, from this example as well, that just by different ways of adding these harmonics up, in all of these cases, it's the same underlying five harmonics. It's actually the same system being observed from different directions and different orientations. But in some cases, you might see very little precession, and in some cases, you might see quite a lot, just based around where you're observing the system from. So this all sort of motivates the method we want to use, but we first wanted to ask the question, well, how many harmonics would we actually need if we were trying to search for these precession systems, if we were trying to find them? Now, there's an infinite number of ways you can ask these questions, and someone's always going to say, well, you didn't use the right example. But we chose arbitrarily a neutron star black hole system where the first mass might be around 10 solar masses and the second around 1.5. With aligned spin components of around 0.3 on both bodies. And then we varied the precessional components of the spin from very small in the top left case to very large in the top right. And we saw that in the case where the precessional spin was small, we then generated effectively a lot of observers. So looking at it from all the different directions and just asked, well, for all of the observers, how many harmonics do you need? And then histogram that. And we see that in most cases, one harmonic would be enough to get most of the power, but there's a significant number of systems, around 20%, where you'd be losing around 5% of the signal power if only using one. If you were using two harmonics for this case, you'd pretty much recover all of the signal power regardless of where you're looking at the system from. As you increase the precessional power, one harmonic is not enough in at least 60% of the cases now. And two harmonics is maybe not enough in maybe 5%, like a small fraction. It's probably good enough for most cases, but there's a few observers going, well, I probably need three harmonics if I'm going to see this well. As you start making the precession larger now, for a significant fraction of observers, maybe as much as 30%, two harmonics isn't enough. 3 or 4 still is enough. And if you go to almost a maximal case, you begin to get positions where some observers are saying, well, I actually need 4 harmonics or more to be able to get all of the power from this system very well. So, as perhaps is not surprising, as you increase the effective precession, you need more and more harmonics to be able to describe the system. So it sort of motivates a search method where perhaps we would build a template bank covering this precessing space, but then filter with an increasing number of harmonics based around how intrinsically precessing that system is. And that's what we've implemented here, which is effectively based off of looking at these plots and going, well, where does it cross this line for 97% of observers, and then deciding that that is the number of harmonics to use.
About 2.5 minutes left.
Sorry?
2.5 minutes left.
Okay, wow, sorry. Okay, so we have built a template bank to search for this. We use stochastic placement to do it. We do this using all the 5 harmonics. We try to reach 0.97 minimal match. We did stop the generation once we had around 400,000 templates just to demonstrate the method. Here's the spin range, here's the mass ranges. It's basically a neutron star black hole with full range of spin, and we use the IMR Phenom XP waveform model to do this. Here we can see the coverage of the template bank. So if we look at the bottom plot here, we can see how well the template bank does as you increase the number of harmonics. The blue line is if we just use an aligned spin bank, and we see that this does very badly. If we only use 1 harmonic, it pretty much matches that. So that's a nice sanity check that this works as expected. If we put in all 5 harmonics, we do a pretty good job of recovering our precessing signals. It's probably not realistic at this point to be able to filter with as many as 5. We can probably only go up to 3 given computational constraints at the moment. And here's the performance of our template bank when we do that. We can see a breakdown of what fraction of templates would be filtered with 1, 2, 3, 4, or 5 harmonics if we could go up to 4 or 5 at the moment. And you can see that as the precession and the mass increases, we need more harmonics, and that's just a function that the precession increases as you go to these higher spins and higher mass ratios. So we've implemented this in an actual search. Here's just some plots that demonstrate we've done that. We do need a chi-square test if doing an actual search on actual O3 LVK data. We do have a chi-square test based on previous work for doing this, which we apply directly. The real punchline of this plot is it works. It actually works really well. So we don't have issues distinguishing glitches from real signals. But the distribution of signal to noise is much larger when you allow the freedom to match multiple harmonics. So if we had we might, with our line spin search, only have 100 triggers with an SNR of 8. If we were using 3 harmonics, we might see as many as 10,000 triggers. So of course, the false alarm rates at a given SNR are decreasing or getting worse because we're filtering with more harmonics. So we can ask, how much better is this search doing if we use reweighted SNR? Again, these are real injections on real data in LVK03. And we can see that if we use 2 harmonics versus an aligned spin search, blue is good and red is bad, and it's blue everywhere. In some cases, we're seeing as much as 100% more signals in some regions of parameter space from doing this. If we try to filter with 3, it's a bit blue and it's a bit red. We start to struggle with the noise background, and indeed 3 harmonics is not better than 2 if we just use a combined signal to noise ratio as our statistic after including chi-squared and stuff. Luckily, ranking statistics have come a long way in the last 6 years. We've gotten better at doing what I would call a semi-coherent ranking statistic, which includes information like signals will see certain phase differences with respect to each other. Hanford and Livingston in particular are inverted, so they'll pretty much see an inverted signal. And if you account for all of this, as we've learned how to do in aligned spin searches across the various LVK pipelines that do this over the last 6 years, it's hard to do this for precession. There's a lot of details in the paper about how this is done that I'm not even going to try to go over in a talk. But we've taken a first cut at doing it, and I think it's a good first cut. I think Connor I'm not going to claim any credit for that. I think Connor did a really good job of this. But if we try our new semi-coherent precessing ranking statistic, we now see that actually our sensitivity using 3 harmonics is increased by, in some cases, more than 100%. And it increases across the parameter space. So we're not losing sensitivity to those NSBHs that show weak evidence of precession. And now, we are seeing an improvement with respect to the 3 harmonic search with respect to the 2. So to wrap up, this precessing search question has been an open one for over 20 years. I do think that this is perhaps the first approach that's practical. I do hope to be running this on 0304 soon, but it is still data intensive. I did try to run this and got an email from the LVK sysadmin saying that I was a third of the internet traffic in a major European country from all internet users, like everywhere. So I clearly need to resolve that a little bit. But really, perhaps my takeaway message, there's some bells and whistles here to sort out. It isn't a final version yet, but I think we're close. I think a little work is needed, but it is runnable as is. But if we really want to observe precession, why are we looking for hints of it in our parameter estimation results? We aren't searching for it. We really need to search for systems that are precessing if we want to be confident that we can find them. Thank you, and apologies if I went over.
Thanks, Ian. We do have time for, you did go over some, but we do have time for a minute or two if anyone would like to ask for a question or two. Yes, go ahead, David.
Hi, Ian. As you said, very long-standing problem and great to see some work towards the resolution. So this harmonic approach, I guess, in principle, would be sensitive also to any other sort of non-standard signal, something eccentric or lensed or violation of TGR. But then with your ranking statistic, you probably filter out some of that.
Yeah, I mean, as with other searches, it is possible that this will pick up astrophysical signals that are not necessarily precessing. I think the final word on what this is it precessing or not, would probably still lie with parameter estimation. We'd be able to observe those highly precessing systems first, but it would still be thrown to our detailed parameter estimation pipelines that would then be able to check for, does it have support for eccentricity or vice versa? And that's the same as with the aligned spin systems that we observe today, except we'll be throwing things over that are actually likely to be precessing. At the moment we are missing perhaps some of the more interesting systems. That's, I hope that makes sense.
Yeah, I agree with that, but I was actually thinking in the other direction, considering the broadness not as a bug, but as a feature. Do you think this multi-harmonic approach is also promising to search for other types of unusual signals?
There's some limits to this, which is sort of along the lines of it doesn't allow for any subdominant harmonics. So, for example, higher order modes, this doesn't work at all because I can't include any of them. I'd have to think about eccentricity. My take is possibly not, but I haven't really thought about the eccentric case at all. That's one of the odd cases I guess I've never worked on. I'd be interested in it, but yeah.
Okay, thank you.
Okay. Oh, I see Carl. You have a hand. Go ahead.
Yeah, just very quickly. I was just wondering. So these harmonics, when you combine them, is that giving you the strain that you're trying to observe, or is it giving you the phase?
It does. So the 5 harmonics, can be expressed as time domain waveforms, and adding them up will give you the time domain H of T that you're searching for.
Okay.
As implemented in the search, there's some shortcuts and things, but the big picture is, yes, these are 5 time domain waveforms. You can add them up with different combinations, and you'll get the H of T that you're searching for.
Okay. So I was just trying to relate it to what we do in CW, and that's sounding like, the statistic will be maximized over basically a linear combination of the waveforms, and then we still have to worry about the phases, but I don't know if it's the same sort of thing.
There's certainly similarities to this and the S-statistic problem, and I guess in how that was considered in the past as well. If you were comparing it directly with F-statistic, you've got effectively 4 components, 2 amplitudes and 2 phases if you want. Whereas if you go to 5 harmonics, you get 10 in a single detector. So more than 10 if you've got more than that detectors, and then it kind of blows the F-statistic problem up, because rather than having 4 well-constrained parameters over any number of detectors, which is always relates to a physical solution, it may be unlikely, but it always relates to one. In this case, you'll have way too many parameters, and it will not be constrained to a physical space. So that was sort of, if you were thinking of coming at this from an F-statistic perspective, that would be where the problem's always been with this, that simply the intrinsic parameter space is too large.
Okay. Oh, thanks for that.
Okay. Great, thank you very much. Okay, we have a short break built into the schedule. I guess we have about 6 minutes before we're scheduled to resume at 10 minutes past the hour. So please feel free to stretch. We will stick to the schedule. Don't go too far, but if you want to get up and move around and get a snack, now's a good time. Let me reset my timer. Okay, I think we can get started again. All right, so next up we have Liana Rauf talking about exploring binary black hole merger populations, I understand, with galaxy modeling. So please go ahead and tell us that.
Thank you very much. So hi, I'm Liana. I'm a third-year PhD student at the University of Queensland. I'm currently here in Perth at the moment, at the UWA. So I'll be talking about my first paper on exploring binary black hole mergers and host galaxies with Shark and COMPAS. So I'll just start off with the two main motivations for this paper. So as I'm sure everyone's seen this graphical table of all the events since 2015. So we would expect with more observing runs, this table will grow, and that's really exciting because this can actually help us constrain stellar evolution models. So I've just got an example here showing the probability of a given primary mass. So it's just the primary mass distribution, and this is just one of the models based on some underlying assumptions. But there are also a few other models that have been looked at in the LIGOVirgo collaboration. So I think with GWTC1, they said the truncated model was the best fit, but then with GWTC2, they found that the power law plus peak model was the best, and that was to account for, I think, dynamical formation channels. So yeah, that's really exciting that with more data we can start constraining these models. So this is more of a bigger picture motivation. So this is more cosmologically related. So we've currently got this H0 tension. So where our prediction for this early root here, so we've got this discrepancy between the early root and the late root for the Hubble constant. So basically what we can do is that we can start using gravitational wave probes to resolve this. So a single measurement of a gravitational wave event can actually tell us if there is some sort of issue or bias in our approach to measure these H0 values, or whether there's some new physics involved here. So there's already been some studies done. So this is with the binary black hole, GW190814. So this is where they've used the dark siren technique. So we've got this DES footprint here and the localization volume for two different events. And then on the bottom right, we've got what they've done here is they've combined the information. So they've combined the redshift information in those localization volumes with the information they got from the signal, so the luminosity distance. And they've combined that to get this posterior probability or the conditional probability for the H0. So you can see that they've, for the binary black hole case, it's quite a flat distribution that just comes down to this large localization volume. So this is where my project comes in. So currently the localization of these binary black hole sources is not accurate. So we need a more efficient way to trace these events and their host galaxies to constrain this volume. So the question I've asked in my work is, how can we predict where these sources are most likely to originate to improve the follow-up of these events? So for that, we need simulations. So I'll just quickly go through some literature review. So there has been some work done on this by Maria Artelli, where she's looked at the merger rate. So this is the number of gravitational wave events per year as a function of host galaxy properties, using the hydrodynamical simulation EAGLE. So here we've got the number of gravitational wave events for binary neutron stars. We've got the stellar mass, star formation rate, and the metallicity of the galaxies. So if you were to do a follow-up of these, you'd want to be targeting these high mass, star formation rate, and metallicity galaxies. So I'll start off with the simulation that I've used. So Shark is a semi-analytic model. It essentially solves a set of differential equations that describe the exchange of mass and momentum within the galaxies and the halos. And then it outputs these properties. So as I mentioned before, the stellar mass, star formation rate, and metallicity of the galaxies. And you can also use that information to get the spectral energy distribution. And from that, you can get information on the photometry, essentially. So on the left, I've got a plot of the star formation rate density as a function of look-back time. We see sort of this discrepancy here, sort of early redshift to rest of 0. This just comes down to, sorry, I should explain. The blue line here is from Shark, and the red points are the observational data. And I've also included sort of this famous Merdau-Dickinson star formation rate fit. So there is a discrepancy here, and that just comes down to the fact that Shark overproduces stars in their disks. If they were to fix that, I believe they'd have to shift the they'd have to adjust the accretion in the disks, but that would sort of mess up their stellar mass functions, and we don't actually want that to happen, because I'll show you later that we actually get a very strong correlation with the merger rate and the stellar mass. Here we've got the R-band luminosity function. So again, here we've got some discrepancy with the observational data and the Shark simulation. I don't think there's anything physical there. I think sort of down here, I think they've just got, they've used a smaller volume, so the number density is a bit higher, and sort of in the fainter regions, there's some selection effects going on. So I've got my galaxy simulation, and now I want to populate those galaxies with binary black holes. So for that, I've been using COMPAS. So this is a compact object merger, population, astrophysics, and statistics. And this is a really useful tool for modeling the physical processes that govern binary formation and evolution. So what I've done is I've started off, I wanted to make sure that the binaries that I produced, they've reflected the environment that they're born in. So I made sure that they were assigned the same metallicies that were assigned to the Shark galaxies. So I take those Shark galaxy metallicies and I input that into my COMPAS along with other input parameters. And then it outputs the properties for those compact objects. So this is just an example here showing the coalescence time. So this is the time between where the binary black holes form to when they merge. I'm just showing their distribution in different metallicity bins. Okay, so I've got my Shark galaxies, and I've also from COMPAS, I've got my binary black hole and their properties. So I've got their remnant masses, I've got their evolution times. So I'm just going to show a simple example of how I put this all together. So I'm going to populate a galaxy M with COMPAS binaries, and I'm going to track the evolution from snapshot I all the way to snapshot K. So to go from the binary black holes being formed to when they evolve into binary black holes, I would just need to find the birth time from COMPAS. And then to go from the snapshot where they form binary black holes to when they merge, I just need to use this coalescence time. And I can do this for every single binary in every single galaxy in every single snapshot. So I just keep trace of all of that. And this is what I get. So this is for a single galaxy. I can look at its merger rate history. So on the top left, I've got the star formation rate from the galaxy itself. At the top right is the coalescence time distribution for all the binaries that have been in that galaxy within the simulation time. And then bottom, we've got the merger rate. So this is the number of binary black hole mergers per year as a function of look back time. So you can see that the merger rate actually follows the star formation rate shape fairly well, but it is sort of stretched out, and that comes down to these delay times that we have. So it's stretched out towards redshift 0. So I've got my merger rates for every galaxy in the simulation, but I actually want to find the observed merger rates in my light cone, in my Shark light cone. So what I do is I take the galaxy ID and I cross-match that to the light cone. I find that observed redshift of the galaxy in the light cone, and then I would interpolate this plot to find the observed merger rate. And I can do that again for every single galaxy in the light cone. So this is one of the plots that I can get. So this is just a hex bin plot showing the star formation rate versus the stellar mass. And each of these hex bins is the average observed merger rate. So you can see a clear trend, so the increasing merger rate with stellar mass and with star formation rate. And I've also done some fitting in the paper where I've looked at, I used a hyperfit function to fit all the different host galaxy properties, and I found the strongest correlation with the stellar mass. And again, for follow-up, you'd want to be targeting galaxies sort of above, to the right side of this red dashed line. And I can verify this result using a color magnitude plot. So the R band, I think it's a proxy for the stellar mass. So again, you'd want to be targeting, bright, like you can see again here that the merger rate's higher for those bright galaxies that are actively forming stars. So I can look at the properties for the individual galaxies, but I can look at the properties as a whole for the entire simulations. So this is where I've looked at the volumetric rate. So this is the number of binary black hole mergers per year per unit volume as a function of redshift. So excuse me. So you can see for our default case where I used this Fryer remnant mass prescription in COMPAS, I see that this overpredicts the merger rate compared to the GWTC prediction. So that's the gray lines here. But when I switched to the Muller-Mandel prescription, I found that this was a closer fit at redshift 0. Yeah. So one of the applications I've looked at is, again, I'll come back to this dark siren technique. So where you've got the luminosity distance from the gravitational wave signal plus the redshift information in the localization volume. And then combining that, we can get this the Hubble constant. So one of the limitations of this is that some of the galaxy catalogs, current catalogs, only cover a small fraction of localization volumes, and these catalogs are also incomplete with redshift. And some of the things I'm interested to look at in the future is that how these incomplete galaxy catalogs would bias this dark siren technique. So this is where I want to look at if there are any sort of statistical anomalies within the method. But that is future work. So one of the applications I've looked at is this the merge rate completeness. So what I've done is taken my Shark simulation. I've taken the selection effects from different galaxy catalogs, so DESI or LSST, Foremost, and I've applied those selection effects to my Shark galaxies. And then I've gone back and worked out what I'd get for those, for the total merger rate. And then I've just taken the ratio of the two. So you can see that with the photometric surveys, which just have the magnitude cuts, these are very complete up to 2 gigaparsecs. Whereas with the spectroscopic surveys, which have a color and magnitude cut, they have a really steep decline as you go towards 2 gigaparsecs. So you can see here the LSST is probably the most ideal for tracing these high merger rate galaxies. So I've looked at what sort of
by the way, about 2 minutes left.
Thank you, I'm nearly done. So I've looked at basically the merger rates we'd expect given certain color and magnitude cuts, but I can also flip this question around and ask, okay, if we were to design our own galaxy survey, what magnitude cuts would we need to obtain a certain completeness in our total merger rate? So if you wanted to go up to, say you want to observe 75% of gravitational events within up to a certain distance, what magnitude cut would you need to go up to? So this is what I've shown here. So I've got this R band magnitude cut. I've got the R band magnitude versus distance again. So these box plots here, each of these lines would, so I've got 50%, 75%, and 90% completeness in the merger rate. So, and I've also included the LSST and DESI cuts as well. So again, you can see that LSST does a really good job out to 6 gigaparsecs. It'll be 90% complete. You'll be able to observe all the galaxies that would contain 90% of the gravitational events at that distance. And then we've also got the DESI legacy imaging survey that would be 90% complete up to 2 gigaparsecs. Yeah, so overall conclusion here is that LSST is probably the best way to go. The wide, fast, deep survey specifically. Okay, so just to summarize, I've generated a population of binary stars and tracked their evolution until they merge. So I've developed a model for that relationship. So the relationship between the binary black hole merger rate as a function of the host galaxy properties. So that's stellar mass, star formation rate, and metallicity. And I've done that for various COMPAS inputs. And for future work, we can also start using the simulations to look at the predictions for future galaxy surveys and how that could potentially bias the H0 measurement. Thank you. And I've also included a QR code if you are interested in looking at my paper. Yeah, so feel free to contact me. And I just wanted to acknowledge a few people that have helped me with Shark and COMPAS over the past few years. Thank you.
Okay, perfect. Thank you. We do have time for questions. And as a reminder, you can raise your hand or during any talk, you can type a question in the chat and we'll get to it. So do I understand? I was wondering about this when you were describing it. So you're using the modeling both to connect information about expected merger rates for a given galaxy, and also to get the photometric properties of the galaxy that you would connect with the observed properties of cataloged actual observational galaxies. Is that right?
Yes. Yeah.
And is that just a matter of like what photometric bands or what comparison do you make photometrically to make that connection?
So I've mostly been looking at the typical one, like the RGU bands. So in terms of connection, what do you mean by that? Sorry.
Oh yeah, like is it a particular color by comparison particular bands, or just luminosity in a particular band, something like that? Like in the old-fashioned days when people would talk about blue luminosity basically as galaxies as a tracer of expected merger rate. And so now what you're doing is to try to make that more sophisticated or more refined. So do you characterize galaxies by some sort of like color comparing different filter bands or anything like that? I'm just wondering if it's a kind of a simple or sophisticated or somewhere in between characterization of the galaxies.
No, I haven't really. It's just been trial and error, to be honest, just looking at any sort of combination of color magnitude cards to see any sort of distinct features. I think anything where you can clearly see that there's a region where there's higher merger rates compared to other regions, and then just using that to figure out what sort of cutoff we'd expect. And yeah, it's all sort of subjective, especially if it depends on what your goal is if you were to design your own sort of galaxy survey, I guess. But at the moment, it was just trial and error and just going through literature and looking at what other people have done. So yeah, so as I showed before, like Maria Telly, she mostly looked at the R band cuts and stuff. Yeah. Okay, got it. Carl, go ahead.
Hi, Liana. Nice talk. On one of your earlier slides, you had this. There was a plot of like merger rate versus your look back time. I was wondering, there was quite like a pronounced spike in that plot. I was just wondering, as a naive question, where that one. So the plot on the top left, where's that kind of spike come from? About sort of 6 to 7 gigayears.
Yeah, it's all a bit random. I've just picked a galaxy from the Shark simulation. I'm assuming it's probably just from any sort of starburst that's happened at sometime before then.
Okay, thanks.
Okay, any other short question? All right, if not that, thank you, Liana. And we
Thank
will
you.
move on to the next talk, which will be by Matthew Mould from comparing gravitational wave events to astrophysical populations.
Okay, hi everyone. I'm Matthew Mould. I've just finished my PhD at the University of Birmingham in the UK, and I'll be moving to MIT later this year. So what I want to talk about is placing gravitational wave detections in an astrophysical context, and hopefully trying to answer the question, if I have a model of compact binary formation, is a particular detected gravitational wave source consistent with my model of formation? So the way we start out is typically, we have a collection of gravitational wave detections. This is the mass ratio plane from the previous catalog. And depending on what you're interested in, there might be a few events that stand out to you in this plot. So 1905-21, because it's the most massive, 1908-14, because it's got a very precise chirp mass and a large mass ratio. And then the bulk of the detections here, there's one in particular, 1904-12, which also has a large mass ratio. So by eye, you might be interested in looking at these events and saying, these look a bit interesting. How did they form? How did they get there? It's not just the masses that might pick out an event for you. It could be the spins as well. So there's this one event from the latest catalog, 200129, which, depending on how you analyze the data, has evidence for large and tilted spins leading to the GR effect of spin precession. And it's also measured to have a large recall velocity for its remnant. So again, this might be something which picks out this event as interesting to you. So what we want to ask is how did this event form? And is it consistent with the simulated models of formation that I have? So things like population synthesis codes, like Liana was talking about in the previous talk. So what do we know about these gravitational wave detections? Well, it all comes from this Bayes theorem, right? So we analyze some GW data D, so that's the actual noisy strain data we have, and we want to infer the properties of the source, so the masses, the spins, the sky localization, distance, etc. And we do that by first imposing some prior model, which is what we believe before we take any measurements. And we update that prior with the likelihood, which is essentially what maps from your model parameters to your observable data. The goal being to make a posterior measurement, which hopefully is somehow constrained away from the initial prior that you imposed. So these are kind of the variables and the distributions that fold into learning what we know about a gravitational wave event. But what don't we know? We don't know how the gravitational wave signals that we see actually got there in the first place. We don't know how the binaries form. And this is something which is not directly observable, so it's something we have to model. The issue is there are lots of different proposed formation channels to produce merging compact binaries. They have orders of magnitude at different rates, many of which overlap with the observed rate by the LVK. So how do we compare all of these models of formation to try and place some constraints and saying these ones might be better at describing these particular signals that I'm interested in than others? So one method which is fairly common because it's simple is the following. So let's say I make a posterior measurement, that's the black curve in this corner plot. And let's say I have a simulated model of formation, so something like a population synthesis code, which produces discrete synthetic mergers. So those are the blue dots in the corner plot. How can I tell how consistent is this posterior measurement with my model? Well, one thing you can do is you could just define some region of my measured posterior. That's this red region. It's typically people choose something like the 90% credible interval in each univariate marginal of this posterior, and then form the region in the high dimensional space as just the Cartesian product of all of those marginals. So in this case, you have these two intervals, you take the product and you get this red square in the bottom left.
And then you can count the fraction of my simulated mergers, which lie inside this region, which I take to define consistency between the model and the posterior. And if the fraction of the total simulated mergers is close to 1, then that's saying, okay, I think my model is consistent with the posterior because many of my synthetic mergers match up with the measured parameters of a real event. But this is bad for various reasons. One, we kind of just arbitrarily chose what this red region was. And it's not a true representation of, let's say, I took the univariate 90% credible intervals, but it doesn't match the real 90% credible interval in this 2D space here. It's also neglecting the fact that we inferred this posterior in a Bayesian framework. So the prior that we imposed isn't taken account for. We're neglecting all of the posterior information outside of the red region that I chose. We're also neglecting any gradients in the posterior inside the red region. So all of these simulated points that lie inside it are taken to be weighted equally, basically. And you can also see that this method will fail for high signal to noise ratios. So for a high SNR, this black posterior gets more and more narrow. And so our red region is going to get smaller and smaller, but our simulated population stays the same. So as you go to higher SNRs, the fraction of your simulated mergers that lie inside the region you chose is going to go to 0, even though your posterior may lie fully inside, the extremal synthetic mergers from your simulated model. So even though by eye you would say my posterior is consistent with my model, you end up concluding that it's not. So what should you do? Well, we're working in a Bayesian framework, so we should work with a Bayesian solution. And the answer is to compute a Bayes factor, which is basically just a marginal likelihood ratio between 2 terms that we saw on a previous slide. So let's say I label my astrophysical model, my simulated model A, and the original parameter estimation prior that was imposed is U. This likelihood ratio is just this ratio of evidences, but we can write it in terms of quantities that we know. So we know the 2 priors because those are things that we choose, and we have the measured posterior. And so we can compute this integral with a Monte Carlo approach. Typically in public gravitational wave data, we have discrete samples drawn from this posterior. So we can compute this integral as a Monte Carlo expectation value. Typically, we're not interested in comparing an astrophysical model to the arbitrary, uninformative parameter estimation prior. So you can compare 2 astrophysical models just by taking the ratio of 2 Bayes factors, which is equal to this ratio of 2 evidences. And basically what the Bayes factor tells you is that if it's greater than 1, the model which I put in the numerator here is preferred in describing the data compared to the model in the denominator. So I have 2 astrophysical models. You want to know which one better describes this particular individual gravitational wave event. You compute these 2 quantities and you make that conclusion. A quick aside is that we're computing Bayes factors, which are likelihood ratios. In principle, what you should do is compute posterior odds, which means multiplying this Bayes factor by some priors. But typically, we don't know very well how to set a prior on a model. So before I take any data, which of my models is preferred? We typically don't know how to do that. And so we set equal prior odds. But we have to bear in mind that our results are sensitive to that choice of prior. So if I had imposed a different prior, I might have made a different conclusion about which model I prefer. So just something to bear in mind when we default to equal prior odds. There's one more thing to account for, and that's selection effects. So the event that we've chosen to look at is not just part of that global population of merging compact binaries out there in the universe. It's part of the subset which is detectable, because indeed we detected it, so we know it's part of the subset of detectable sources. Our detectors mean that we're more sensitive to heavier sources that are closer to the detectors. So the detectable distribution is different to the full intrinsic distribution. So we need to account for this fact. And there's a simple way you can modify the base factor to do this, and that's to condition your marginal likelihoods on the fact that this data is from a detectable source. And essentially, you just introduce these weighting factors, which if you have a simulated model A, this weighting factor is the fraction of synthetic sources from my model, which would be detected if I fed them through the actual search pipeline. So you're just kind of renormalizing the distribution of sources from your synthetic model to account for this detectability. Okay, so now we apply this to a couple of cases. The first case was formation of merging binaries in young stellar clusters through three-body interactions. So in this left plot, I'm just plotting actually the distribution of synthetic sources from the simulation. Those are the blue, orange, and green curves from different types of three-body interactions. So whether there was a tertiary which kind of came into an existing binary and took out some of its orbital angular momentum in order to accelerate the merger, or whether an interloping third body actually exchanges with one of the components in an original binary. And so depending on these kind of different subchannels within this three-body young stellar cluster formation scenario, the distributions of the source properties are different. And so in this example, we want to compare these different formation scenarios to GW 1905-21, which you see with the purple contours. So just by eye, you might expect that 1905-21 seems to be the most consistent with this orange distribution. So let's put that, let's quantify that with the base factors. So remember, the base factor is a relative measure, so we always have to compare one model to another. So in this case, we're always going to compare to this tertiary flyby scenario. So that's why the base factors, the log base factors, are 0. And indeed, if you do the calculation, what you find is that this blue subchannel, sorry, this orange subchannel is the one which is preferred over the others, but not necessarily strongly. We apply this to another scenario, which is that of
about 3 minutes left.
Oh, thank you. Of hierarchical mergers. So by a hierarchical merger, I mean a merger in which one component of the binary is a black hole, which has already undergone a previous merger. So we have this very simple toy model code called cluster for quick cluster, which can produce these synthetic populations of hierarchical mergers. But I stress that this isn't really astrophysically motivated. It's kind of a toy model just to illustrate the idea. And in this case, we're going to look at not just two mass parameters, but Chirp mass ratio and two effective spins, and compare that to two different gravitational wave events, which some people might argue could have a dynamical origin or contain a hierarchical black hole. So we do the same thing. We quantify these numbers and compute base factors for 1904-12, because it has a large mass ratio, a mass ratio away from unity. That's what you see in the brown distribution here. It's most preferred to be a 1G plus 2G. So a merger between one black hole, which was born from stellar collapse, and one which has already gone a previous merger. And that's because these 1G plus 2G sources typically have more unequal masses. So they best match the observation of 1904-12. For 1905-21, we find that high generation mergers are much preferred. But this is all subject to our modeling choices. So, for example, in these hierarchical merger simulations, we chose an upper mass cutoff for black holes born from stellar collapse. This is corresponding to the parent instability mass gap of around something like 50, 60 solar masses. So anything above that can't really be described as a first generation merger in this model. And so for this reason, 1905-21 is strongly preferred to be a high generation source. But this just kind of illustrates, if you have features in your simulated distributions that can't match your real event, it's going to become very clear when you compute the base factor, because you get these very large numbers. Again, these are just toy models to illustrate the methods. So to summarize, if you want to test whether an event which for some reason is interesting. Maybe it has large masses, large mass ratio, large tilted spins. You want to test if that's consistent with a particular formation scenario. What you should do is simulate that scenario and basically compute base factors between different simulations, conditioning on source detectability to make sure we remove that bias. And this is basically going to allow you to conclude which of my simulated models is preferred in describing that data. And that's all. Thanks for listening.
Okay, thank you. We have time for a few questions. Let me just check one thing. So on one slide, you had both 1904-12 and 1905-21 on the same slide, but you're still focusing on event by event model comparisons, I think, right? Or do you are you also looking at like the collections of models that you would get from assuming a common formation channel?
Here we're specifically targeting single source inference. The point being, well, if you want to combine everything together, what you should do is a hierarchical model and do population inference. But here the idea is people who make these simulated models, so people who do population synthesis, for example, are very interested in finding out, can my model, if I run it forward, can it reproduce something that's similar to something that we've seen? And that's inherently a single source inference. And that's why we're focusing just on individual sources, irrespective of the rest of the catalog.
Got it. Okay. Christopher, go ahead.
Hi. So it was just a related question to that. So obviously we know if we want to compare to the entire population, that would give us the most information, because that would include both the events and the things we didn't detect. I was wondering though, in the limit that you apply your approach to each individual event in a catalog, would you end up as the same result as doing it at the population level? Or does it miss out on the sort of the non-detections being factored in?
Well, I think the non-detections come in through the inclusion of the selection effect. So because the events in our catalog are taken to be independent, if you want to compute the evidence for, so the likelihood of all of the data is just the product of the individual likelihoods. So maybe what you can do is compute this base factor for the individual sources and take the products, but I'd have to write it down and double check that that's actually valid.
So you probably would also want to allow for multiple channels and not assume that everything comes from the same channel in one way or another.
Yeah, so the assumption going into this would be that everything is collectively described by these two models that you're comparing, which you don't want to do in the full population inference.
Okay, another question? All right, well, thank you, Matthew. And
Thank you.
we have another 10-minute pause in the schedule now. Let's see, so we will come back on the hour in about 10 minutes, 11 minutes, and see you all then. I think we're ready to resume now. So Christian, if you're ready, let's please go ahead and tell us about EMRI population and LISA observation.
Sure, thanks. Hi, so I'm Christian Chapman-Bird from the University of Glasgow, and I'm going to talk today about constraining EMRI population astrophysics with LISA observations. So I'd like to kick things off by saying thanks to the organizers for giving me the opportunity to speak today. And let's begin with a brief overview of LISA. So LISA is a gravitational wave detector that will be launching hopefully in the 2030s, observing in the millihertz regime for a number of years. And we're expecting to see a number of interesting gravitational wave signals from different sources. So the source that I'll be talking about today is this one down here near the bucket of the sensitivity curve, which is displayed by these harmonics. So these are extreme mass ratio inspirals. So extreme mass ratio inspirals consist of the inspiral of a small stellar mass compact object into a large massive black hole. So they're complicated systems with evolution that spans a number of years, and the complexity of the waveform gives you a extremely precise measurement of the parameters of the system. So this lets you do a number of very interesting things. So you can do things like test general relativity in strong field limits, and you can measure very precise information about all kinds of things like the initial eccentricity of the inspiral and things like this, which gives some nice hints into the ways that these systems form. And we don't know exactly how many EMRIs we're going to see. So the paper I've linked there at the bottom, the rate estimates are deviating by roughly 3 orders of magnitude. So there's quite a large window of potential numbers that we expect to see, but there's a strong probability that we will see sufficient number of EMRIs to infer some properties of their populations. So this is something that we want to prepare for, and we want to think about the kinds of things that we could hope to learn about the way that these systems form. So let's talk a little bit about how this works. So obviously, in order for an extreme mass ratio inspiral to happen, we've got to get a compact object into an inspiraling trajectory around a massive black hole. So if you can imagine in the center of a galaxy, for example, in a nuclear star cluster, we have distribution of stars surrounding and compact objects around our massive black hole. And through two-body interactions and other dynamical processes, these compact objects are kicked onto an inspiraling trajectory. So we need this. There are some various facets to this based on exactly the scenario that you're thinking about, but in general, we need this scenario in order to produce extreme mass ratio inspirals. But there are various astrophysical processes that can cause us to deviate from this scenario. So one of these would be something like cusp erosion. So this is where what we call a dense stellar cusp around the massive black hole is disrupted by a similar massive black hole coming in. And when these two when this close to equal mass merger happens, the resulting distribution of stars around the remnant is disrupted and needs time to relax. So on the right hand side, I'm kind of depicting this by saying that there aren't really very many compact objects, and so you're going to have an extremely highly suppressed EMRI rate until the compact objects and stars can relax back into that cusp. So this is one effect that could that we expect to dampen the EMRI rate. Another effect that will cause what we observe to deviate from maybe the true distribution is something like mass segregation. So this is a process over which, during long time scales, if you have a distribution of masses in a scenario like this nuclear star cluster, over time, the heavier objects will sink towards the center, towards the massive black hole, and the lighter objects will preferentially be less so. So you end up with an overdensity of heavier objects near the massive black hole. So this means that we will actually see more of the heavier objects and less of the lighter objects. And so this is something else that we could maybe try and understand a little bit more with extreme mass ratio inspirals. So the big challenge is that these effects are, it's similar to how what Matthew was talking about in the last talk. You can see that the formation scenario actually affects the parameters of the sources you expect to see kind of a lot. So this is also true here. Things like the cusp erosion effect that I just mentioned, depending on how often massive black hole binaries mergers happen, then you're going to have different rates of cusp erosion, and that's also going to couple into how often a massive black hole of that mass merges. So that's another complication. Similarly, how quickly the cusp then relaxes and regrows depends not only on the mass of the massive black hole, as I mentioned here, but also on that what that initial distribution was. For that mass segregation effect, again, the result kind of depends a lot on how the initial distribution of the stars and compact objects were. If you've got a larger tail of heavy compact objects, you can expect these to sink in more quickly, and we may see more of those. So these effects all couple together into what we see. So it's actually going to be quite challenging to unravel all of that, but we can at least start to make some attempt to understand how we would do that. So the way that you might approach this is by constructing a population model, parameterizing these effects, and then using population inference, we can infer the parameters. So, I've kind of explained this process with a little flowchart. So we start with how these astrophysical processes couple into the underlying EMRI population in reality. Then we observe a subset of this with our detector. And then with the red arrow shows going back, we can hope to reconstruct from our observed population, the underlying population, through knowledge of our detector's sensitivity. And then using our population model, we can hopefully learn about the astrophysical processes. So inherently, this process gives you, there'll be some assumption of a model. So you need to be very careful with this, because depending on your model assumptions, you can add a lot of information artificially into this and arrive at constraints which are not necessarily representative, but it's a good starting point for understanding which effects will actually really be coupling into our observations and worth pursuing further. So I'd like to talk a little bit about this specific detectability part here. So this is actually quite challenging to model. So in the absence of choosing any particular EMRI detection pipeline, mostly because they don't really exist yet, we can approximate the detectability in an event by considering its signal to noise ratio. So the way that you would correct for selection effects is by understanding for a given population what fraction of the population is detectable and reweighting based on this. So you need to be able to compute what fraction of a given population is detectable very quickly. But the challenge is that generally speaking, this is only really tractable to perform with a Monte Carlo integration, and you need to essentially evaluate the detectability of millions of samples from a population, and then you've got to do this every single time you want to propose a new population. So if you're doing a population inference, you're going to end up having to, this is going to get intractable very quickly. So for an EMRI, computing one SNR takes on the order of a second. So this is very expensive and challenging to scale up to what's necessary for a population inference, even though, as you can see, the SNR function is pretty smooth and well behaved. So hopefully we can use some approximate tools to speed this process up. So what I'll be talking about is using a machine learning method that is quite old but is very effective, called a multi-layer perceptron, to essentially learn the SNR function for our purposes. So these are universal function approximators, which essentially means that if you make the network big enough and you show it enough data, as long as the function is smooth and well behaved, you should be able to learn it. And we can essentially just generate a large bank of SNRs, tweak the network to improve its performance on that data set, which is known as training, and then we can use it in population inference for the selection bias computations. So this is very efficient with GPUs, which is what we leverage to do this in a reasonable amount of time. So what we find is that we are able to get some really great results that are a lot better than using other similar methods which try and perform the same process but use simpler techniques, so things like just interpolation over a grid. Because the high number of dimensions in the EMRI parameter space, these methods struggle quite a lot, whereas we're able to achieve some great accuracy estimating these SNRs to within one, in the vast majority of cases, so that's great. And you can see that the speed up that we get is going to be sufficient that we can actually tackle this this challenge of estimating the selection biases. So we can do this for not just EMRIs, but any generic problem where you need to do something like this. So I wrote a little package to do this, so you can check that out if you're interested. So with this, armed with this, we can then perform these Monte Carlo selection function estimates and do some population inference. So we actually want to validate what we've done first is we've validated whether we can actually do this by considering a simpler population model where we do not include the astrophysical selection effects. So we need to check whether the selection function estimation that we're performing is 1, necessary, and 2, sufficient. Is it accurate enough, and do we need to worry about it in the first place? So this simple distribution consists of a couple of parallels for the masses and a truncated Gaussian for the massive black hole spin magnitude. And we observe roughly 120 events over 4 years of observation in this simulated scenario. So that last parameter there is the rate R. So this is indicating that we inject roughly 1,000 EMRIs per year, and we observe, well, significantly less. So selection bias is clearly here playing a major role. If you don't include them in your inference, then you are seeing some strong biases that are well above 3 sigma in some cases. So that's definitely motivating considering these, but you can see that it doesn't affect all parameters. So it really does depend on the population model in question. But obviously, if you don't have any tools to check, then you're not going to know whether it matters. So kind of important. But yeah, we were able to, in this specific scenario, we can also just make some predictions about how well Alicia can observe these various features of sample EMRI populations. So we can constrain the parallel slopes, so the mass functions and the spin distribution with very well to within 15% for the mass function and 10% to the spin distribution. And yes, this is essentially the step 1 of this process. So now what we'd really want to consider is how to include the astrophysical effects in our population model, and then we can use this framework that we've developed to then perform the parameter inference to understand how well we can constrain these effects. So I'll put my conclusions up there. So yeah, generally speaking, we are expecting to see enough EMRIs with LISA that we can probe the features of the EMRI population. And one feature of the population that we care about is the formation mechanisms. So by using population inference, we can hope to constrain these various mechanisms and understand how EMRIs form. So we've validated how we're going to approach this problem, and that we have the tools necessary to do it. So the future work will be to then include these astrophysical effects in a parametric population model and see how well we can constrain them. So yeah, thank you very much.
Okay, thank you. Yeah, we've got time for a few questions. Can you remind me how order of magnitude, how many EMRIs we would expect that LISA would observe?
So the most pessimistic. So I mean, it's a hard question in general to answer, because over the last few years, a number of studies have been performed into some of the various formation mechanisms and found that the numbers that we've assumed for the rates either need to change a bit, or there are just new mechanisms we haven't considered. But the most recent study that really tries to do a broad estimate of the rates varies between roughly, the most pessimistic one estimates maybe 1 detection per year, and the most optimistic one estimates on the order of 10,000. So it's quite a large difference.
Yeah, good opportunity for observations to tell us something. So it's good to figure out what they're going to tell us, right?
Yes, exactly.
Kind of connecting with the previous talk, so where Matthew was talking more about, inferring event by event, comparing models, comparing possible formation channels, I guess, by, and then here, let's see, is this an analogous situation in terms of the astrophysics of different galaxies, or is there a commonality that you expect to uncover among the EMRIs, the individual EMRIs, which come from totally different galaxies? I guess that's, is it, are you sampling kind of the different specific conditions in different galaxies, or are there going to be astrophysical processes that would be common? If I'm saying it right. So
you're right. I think that you would expect that. I mean, ultimately, we know that the environment, stellar environment around in the galactic, in the center of a galaxy, varies a lot based on the galaxy in question. So this is an ingredient that probably needs to be considered, which is that you have an array of galaxies, and these, this changes with things like redshift as well. And so if you have a massive black hole within a particular galaxy, we might expect the stellar distribution around it to be different. So I would say that that's probably something that you would maybe want to fold into the analysis, or at least account for the fact that we have there's various uncertainties on how well we understand these things. But yeah, I mean, ultimately you would expect the distributions of extreme mass ratio in spirals from different galaxy types to probably look a little different. Whether we'd be able to pick something like that up is another question. It really depends how many, well, I suppose it depends how many you're able to see, and also the sophistication of your population model, because that ultimately limits what you're able to probe. Yeah, I think that's definitely something to consider. It's not like they will all look the same from all galaxies. You'd also have to imagine that the massive black hole properties and the galaxies are themselves going to be correlated as well. You might expect larger massive black holes to occur in, say, elliptical galaxies, because they've undergone mergers and things like that. So yeah, there's going to be a lot of interesting correlations to consider in this population.
Indeed, yeah. All right, we have a few more questions, a few more minutes before our last scheduled talk, and in case anyone is trying to tune in specifically for that or jump sessions, I think it would be best to wait. So if there are any other questions for either for Christian or for any of the previous speakers who might be online, if anyone would like to speak up, now's we have a few minutes for that. I think, Christian, you can stop sharing now. We will wait another minute or two so that we stick to the schedule. So as we get settled here, the last talk in our session by Jem Sadiq is actually a recording, which Aaron is going to feed into Zoom here. Tom Dent is online to answer questions about this talk at the end, though. So we'll get the recording up to go. Okay, so now I'm seeing.
Hello, everyone. My name is Jam Sadiq.
Great.
And first of all, I want to say thanks to the organizer for providing me opportunity to present my work. I want to mention that this work is done in collaboration with Thomas Dent and Mark. Unfortunately, I am unable to join live, but I am giving this recorded video. And for any question related to this work, I hope Thomas Dent will be attending this session and he will be able to give answer to any question related to this work. So I will be telling you about our recent work on studying merging binary black hole mass distribution with our proposed iterative reweighted kernel density estimator. In my talk, I will give you our motivation, which is do we need to go beyond a power law or universal model for mass ratio to study population properties of binary black hole system from observed gravitational wave data. I'll tell you about our proposed method, adaptive kernel width density estimator, and its improvement with iterative reweighting. I'll give you the application of our method on the two-dimensional rate estimate and some results. And based on results, we have some questions that we want to answer in future. So we know that with the many observation of binary black hole mergers with gravitational wave observation, we can study all of the observations combinedly to see the population properties of binary black hole system, to study their astrophysics, the formation challenge and evolution, and etc. Typically, in this analysis of LVK collaboration, people assumes the power law distribution for the mass ratio, as investigated with GWTC1 result in this paper I mentioned here, where the result was that the two black holes of a given binary prefer to be of comparable mass. But there are technical issues that are related to the mass ratio distribution, specifically the large uncertainty at low mass, and also the correlation of the chip mass with a line spin to have a large, which also have a large uncertainty. With the more observation of gravitational wave up to GWTC3, many interesting studies has been done. Specifically, I want to mention about this paper here, posted here, where they study the mass ratio dependence on the chip mass, the mass ratio consistency with the power law, reduce evidence of rate with the chip mass, and also combinedly reconstructing the rate estimate with the both masses together. So we are trying to answer similar question with our study that I will be telling you today. As a reminder, previously we published a paper in which we introduced adaptive bandwidth kernel density estimator as a non-parametric model to study population properties of binary black holes. In this work, we computed the rate estimate with our proposed AWKDE method and found and here is the results of the rate as a function of primary mass that is shown here. As you can see, our method is consistent with other proposed method and show the features like the other method, except some of the models show a peak around 20 solar mass, which our model don't predict. So in our KDE method, we have a problem with this, which is the PE uncertainty. We know that the values of PE samples that we use to estimate these rate I showed on the previous plot, we use the masses of the systems, but those event mass value are not measured exactly. They cannot be measured exactly. These PE samples are only accurate up to the PE prior population. So because of this prior population assumption, there is uncertainty in the PE samples. And because we use this PE sample to get the population model that we propose, these uncertainty also incorporated in our model. So we want to reduce this uncertainty using a iterative reweighting scheme, which is similar in its spirit to standard expectation maximization algorithm of statistics. So here below, I put the sketch of algorithm that we are proposing for iterative reweighting scheme. So we have a current estimate of population rate density from our method. We use that to draw a random sample from each event PE samples, which are weighted by our current estimate of population rate density. With these reweighted samples, we then train our KDE and compute the new rate estimate. And we use this this new rate estimate to do reweighting step 1 again and repeat this procedure iteratively. So we try this idea onto a Moog data. So here I show you a Moog data test for a power law and Gaussian peak distribution. We choose 60 values from this true distribution as shown in the black dash curve. And those 60 values are from a power law with a peak, and Gaussian peak has standard deviation of 3. Those 60 values have 50% of the samples from Gaussian peak and 50% from the power law distribution. We add random error to those values, 60 values, with a standard deviation of 5. And for that error data, we compute 100 random samples for each event value, errored event value. And then we apply our KDE method without iterative reweighting and got the result on the left. So you can see our without iterative reweighting, our AWKDE method does give the feature of the true distribution, but the peak, height, and width are not accurately measured because of the error in the data. But when we apply our iterative reweighting scheme, it was able to recover this it was able to recover the exact peak, height, and width of the true distribution and reduce this error in the uncertainty of the samples. So with this confidence, we apply our method to GWTC3 BBH events mass values, assuming computing the rate estimate by assuming a power law distribution for the mass ratio. And here are our results. As you can see, we were able to recover the feature as recovered by other parametric models. And this time our peaks are sharper than the previous results. Also notice that we don't find evidence of a peak around 20 solar mass in these results as well. Then we want to apply our method to the 2 dimensions. But one thing to notice that when we estimate KDE, we in 2 dimensions, it doesn't care about the mass to be a primary or secondary, or the mass should be, primary mass should be bigger than the secondary mass. So in order to handle this issue, we are training our KDE on the mirror set of M1, M2 samples. It means that we take M1, M2 samples and get another and add to this another sample labeling M1 to M2 and M2 to M1. In this way, we compute the rate estimate, but if the rate estimate is a smooth function, then the contour must cross M1 equal to M2 line at right angles. And this is what is incompatible with the power law assumptions for the mass ratio. So when we apply this to GWTC3 BBH event, we found this results. So here is our estimate of rate as a function of primary and secondary mass. So we see a clear peak around 35 solar mass for M1, and also for M1 we see a peak around 10 solar mass. Another interesting thing that if you look at the peak around 35 solar mass and look at M2, most of the M2 value after this peak doesn't care about M1, and most of the value lie in the range of 30 to 35. The peak around 10 solar mass is also interesting because here we see this elliptical feature which show that there is an anti-correlation found at this lower mass between primary and secondary mass. If we go beyond that, we see the flatter Q distribution. So this is some interesting result we found. In order to elucidate 2-dimensional result, we compute the 1-dimensional rate estimate from the 2-dimensional results by just numerical integration, and without assuming, and our results are without any assumptions of power law distribution for the mass ratio. We were able to recover the feature as observed in other sample, in other models, and in our previous results. We also find that secondary mass has peak feature as well, and both the component masses have this double Gaussian or peak with a broken power law kind of structure. So we also in order to elucidate how the M2 distribution related to M1 that we see in this 2-dimensional plot, we plot the distribution of secondary mass for a fixed value of the primary mass. So here are results for different fixed values of primary mass. If you look at the right plot where we have more the primary mass large value, larger than 35, we see the distribution of M2 is close to constant. So this is what we see in the 2D result as well here. With these results, we have some interesting questions to look at. One of the interesting question is that, do we expect significant effect on the mass ratio or this two-dimensional rate estimate if we use if modeling spins or we apply redshifts? Currently, we are ignoring the spins because we are implicitly assuming that the spin distribution follow PE prior, and our method is limited to that. On the other hand, another question is that if the power law for the rate for the mass ratio as a function of M1, which is assumed in LVK, is inaccurate, and if it is inaccurate, what are the implications for the spin inferences? Because spin inferences are used to give this assumptions of power law distribution for the mass ratio. Another interesting thing that we want to check is that how far our estimated two-dimensional rate that I showed you is influenced by our KDE model, because our KDE model is the sum of the Gaussian with the identity matrix covariance. So we can check this by looking more Moog data tests if this is the case in our estimate or our model. Another thing is that this anti-correlation that we see around lower mass, this anti-correlation between M1 and M2, this may be because of our KDE model, or is it or our model is not biased because of giving this anti-correlation. And also having this anti-correlation and these results that I showed you, we have astrophysical interpretation to do. One thing can be like pairing, which appears to be weaker than previous. Why? And also this anti-correlation is real, or it is connected to binary dynamics, how it is connected to binary dynamics. So these are the questions that we want to look at. And we will have a paper related to this study out soon. So this can be checked hopefully in few days or a week. And one thing I want to show, I have a little bit of time, although you can see my extra slide with my slides hopefully available for this meeting. So we did this 2D Moog data test where we use a mixture of uniform and Gaussian, bivariate Gaussian distribution, and artificially add an anti-correlation between the two dimension M1 and M2 here. As you see on the left, we have random data, and we compute KDE without iterative reweighting with the error added to the Moog data to mimic this anti-correlation. When we apply our iterative reweighting case, this anti-correlation goes away, as you can see on the right. So this is one of the confirmation that our method it can take into account this anti-correlation if it is fake. So this is all I have. I leave you with these open questions, and I hope Thomas Tent will be there, and you will have a lot of questions to ask related to this work. So thank you very much for listening, and have a good meeting.
All right, we'll virtually thank John for this talk and maybe get that message to him. So right, we do have time for some questions or discussion. Maybe you can clarify the anti-correlation in mass 2 versus mass 1, if I heard it right. It was hard for me to see what how I should be seeing that, but that is taken as a sign of a sign of a kernel mismatch or something like that.
So hi Peter. So maybe, well, I don't know how we should look at a particular slide. I could screen share, or we could.
If you have them, go ahead and screen share. Yeah, I was wondering about that too.
See, share screen. Okay.
Yeah, so I was trying to look at this, but I wasn't sure what I should look at for the anti-correlation.
Let's see. You see slide 9 with this big blue square plot. Okay. So if you look at, let's say, towards the bottom left, you see, well, it's a blob, but it's kind of extended along the diagonal. So this corresponds to, like, if you increase M1, you tend to decrease M2 and vice versa.
And so here you're talking about the purple contour, the purple densities.
Yeah, I mean, the red points are just like median points from the parameter estimation samples. They're not our result. The contours and the purple shading is the actual density estimate. Well, rate estimate.
Of the events in the cataloged events, I see, not of the model, right?
Yeah.
Mhm.
So, okay, we don't believe, because we've done this like mock data challenge, basically the question is, well, is this like diagonal behavior, is it due to the PE errors, which also extend kind of along the diagonal because they're along consoles of constant chirp mass, or is this real? And we did this mock data study to determine how well the method can kind of remove these correlated errors. And it seems to be able to do that. So we think that at the moment this is a real feature, which is kind of interesting. I mean, why should binary black hole, mass 1 be anti-correlated to mass 2 in this region?
I see. You're saying over and above the PE error trend that would be something like this. You think that the population itself has this anti-correlation. Is that what you mean?
Yeah, I mean, well, if our method is working correctly, then that's the result that we get.
Mm-hmm.
But we don't know any particular, let's say, astrophysical reason why this should be the case. But it may be something to do with binary dynamics. But okay, this is fairly speculative. Would be fairly speculative.
Mm-hmm. Okay, thanks. That helps. And Matthew, go ahead.
Thanks. So on this same plot, unlike the univariate marginals, here you don't have the uncertainty, right? This is just one realization. So is this like a maximum likelihood point or something?
Yeah, that's a good question. It is pretty difficult to show uncertainties on a 2D plot.
Yeah.
This is the median, so it's like the point-by-point median. At every point in the plot, we take the median of like 900 iterations.
Is this anti-correlation, if you look at, instead of just the median, if you look at the individual points in the uncertainty, is this anti-correlation always there?
That's a good question. I mean, we could put together some kind of, figure of merit or summary statistic for how much the contours here are anti-correlated, and like see what the value of this is for all of these 900 samples. So yeah, I mean, that's quite an interesting question of how do we tell how confidently it's present.
Yeah, we have some summary statistic that you have some credible interval on how certain are we that there's an anti-correlation. I don't know what that quantity would be, but
yeah, this is the interesting part of these like non-parametric models. It's like, well, it tells you what the population is, it doesn't tell you like what the interesting features are, so you have to invent some way of measuring the interesting features. But yeah, I mean, that would be an interesting thing to try and add. Thanks.
Another quick question I had was,
yep.
So you extended to 2D here. Can you go much beyond 2D? Does this extend to, say, 7-15 dimensions of the quasi-circular binary black holes? Or are you limited to this lower dimensionalities?
Well, it's also a pretty good question. I mean, we want in the next step would be, I don't know if if the slides mention this on the, So okay, I guess it's not mentioned on the summary slide, but okay, the plans immediately are to go to redshift and or aligned spin, so that's 1 or 2 more dimensions. In principle, you can make a KD in any number of dimensions. The problem is optimizing it. At the moment, we're just assuming kind of a circular kernel, well, kernel with like diagonal equal covariance in all dimensions. Obviously, if you like have spin and redshift, that doesn't make that much sense. So it would take a bit more, well, let's say for 3 or 4 dimensions, it would take a bit more computational cost. If you want to go to a really large number of dimensions, yeah, you probably do hit significant problems on that.
Okay, thanks.
All right, any other questions? Okay, then I guess we've reached the end of our session. Thank you to all the speakers. It was a very interesting session, and I hope all the audience members also enjoyed it as much as I did. With that, we'll close and see you all in another virtual environment or in person someday.